Hello, my name is Jong Kim, and I'm here to present our paper titled StableVITON Learning Symmetric Correspondence with Latent Diffusion Model for Virtual Try-on. First, let me explain the task. The objective of virtual try-on is to produce synthetic images that look natural while preserving the details of clothing. Since foundation models excel at generating natural images, our goal is to ensure that the details of clothing are well preserved. So in this paper, for the first time, we propose a network that uses stable diffusion model to learn the correspondence between the clothing and person for virtual trial. There was two main approaches using foundation models. First is converting clothing into text and including it into stable diffusion. This method produces natural results but suffers from a significant loss of spatial information by the script encoder. So it leads to a lack of details like this. And second is using an external wrapping network to wrap the clothing to fit the person and filling the remaining masked parts with the foundation model. But this approach also heavily depends on wrapping network. So to preserve the spatial information of the clothing, we first applied ControlNet. ControlNet is essentially designed to perform image-to-image transformations, and we set up our training like this. However, as you can see in the second column, uh, even with the use of ControlNet, the details of clothing can change. So we believe that this issue arises from due to the limitation of add operation of the ControlNet. While the original ControlNet performs well on tasks like this, where the alignment can be directly extracted from images, the add operation make it challenging to achieve the desired results for virtual trial. Like previous studies, our approach also reconstruct the masked images, but unlike ControlNet, we introduce a new cross-rotation mechanism. As illustrated in this image, the structure performs working within the latent diffusion model, effectively transforming the traditional two-stage process into one-stage process. So the zero cost attention mechanism, as shown in this figure, receives the person features from the original unit as query and key value pairs from the clothing. So this is the visualization of attention map from the zero cost attention after the training. So the top left shows the two input images, and below is an overlay of the generated results and closing attention map. So when zoomed in, the attention map's intensity is visualized. For each query patch, the entire clothing acts as key. So we resize the clothing to match the attention map size for augmentation. It's for interpretation. So and the red V and white V on the right chest area show high attention scores with key patches shifting gradually, indicating the patchwise warping in the latent space. When trained only with Python HD dataset, the closing does not accurately reflect the input as shown in this figure. Due to the high degree of attention operations, we believe that this large amount of data was necessary. So in this paper, we introduced augmentation for the first time for virtual trial. And when augmentation is applied, the attention map is drawn more clearly. However, even with augmentation, the attention map does not converge into one single point. An incorrect color appears like this. We identify the issue as arising from the uneven distribution of potential map weights for query patch. To address this, we propose the attention total variation loss, and total variation loss commonly used in virtual trial studies ensure that predicted flow is evenly distributed during warping. So in our research, we the weighted sum of the attention scores corresponding to the queries determines the final output. So we multiply the attention scores by the grid coordinates to use as the center coordinates, and ensuring these coordinates are evenly distributed. So finally, these images, these laws result in more clear attention map and more accurately generated clothing. And for the first experiment, we first trained and tested on Python HDD dataset. So as shown in the first row of the image fit, warping does not perform well for the complex poses and method like GAN or DCI Python overlay closing on the arms. Method like paint by example or StableVITON still left detail. And previously, the same dataset was used for both training and testing, but in this paper, we used dress code and SHHQ as test dataset to evaluate more diverse set of individuals. So GAN-based methods completely fails in handling the background or closing, and for the others, as shown in the second row of the images, the patterns or arm appeared unnatural. So thank you for listening.